Hi everyone. Today we're solving A-level physics paper 4, October-November 2023, 9702 paper 4-1. The time is 2 hours. We have structured questions for the day. So before we start, let's take a look at the threshold. So for paper 4-1, this is where we are at. Out of 100, we have A at 68, B at 60, C at 49, D at 38, and E at 26. It was comparatively higher. The October-November threshold is usually a bit higher than the May-June threshold because fewer candidates give the exam. That's one reason. So I'm sorry for the long hiatus. I actually took a break from recording content. I'll be releasing more starting this month, and I'll be more free starting from May. So I'll be releasing more content before your May-June 2024 session. So if you have any more requests, please drop a comment down below. And if you like the content, please remember to subscribe to the channel, like the videos, share this with your friends. Also, quick shout out to my patron. So currently we have a lot of members. There are 3 tiers, one for just general support. There's one for solved papers, notes, and requests. This is the most popular tier actually, where you get one-on-one problem-solving sessions over text, and you get access to all physics, chemistry, bio, paper 1, 2, 4, and 5, and math P1, P3, M1, and S1. All my notes and solved papers from 2002 to 2023, all of them. The ones I solve here, basically all of them will be included in a OneNote file. You get access to it as long as you're subscribed. And for the ultimate learning experience, you get one-on-one video meetings with me via Google Meet, where we solve your personal problems once or twice a month, along with all the other perks included there. Also, you get a shout out at the end of the video for all my videos, as long as you're subscribed. Currently, we have 2 members there. Anyway, I think we should start. Also, I changed my microphone. I think the audio should be clearer now compared to before. So yeah, let's write down the threshold first before we start. So this is component 4-1. So out of a total mark of 100, A was at 68, B was at 60, C was at 49, D was at 38, and E was at 26. Okay. So I think component 4-1 is the same as 4-3. Let me check. Yes, it's actually the same variant, component 4-1 and 4-3. But the thresholds are a bit different. As you can see, the thresholds are a bit different because people from different geographical locations give the exam. So the people who gave the exam, who gave component 4-3, scored a bit better compared to the ones who gave component 4-1, although it's the same paper, right? There's absolutely no difference in the paper. Anyway, I think we should start. Let's not waste any more time. I actually have the paper solved, so we won't take long. So let's begin. So starting with question 1. State what is indicated by the direction of the gravitational field line at a point in a gravitational field. Okay. So suppose this is a planet. We know that the gravitational field lines point radially inwards, right? So what do these lines actually indicate? Suppose if we have a mass here, an object with mass, that object will feel force in the direction of the field line, okay? So very important theory. What is indicated by the direction of the gravitational field line at a point in a gravitational field? It is the direction of force acting on a test mass placed at a point inside the field. That's what it indicates, okay? It's the direction of force acting on a test mass placed at a point inside the field. Now, you didn't have to say test mass, it was optional, it's in a bracket. Now, explain with reference to gravitational field lines. Oh, what other theory might you face? Theories might you face? You might face, they might ask you, what do you define a gravitational field line? So that will be the direction in which a mass experiences force. Okay, same thing. And here, what is indicated by the direction? So it indicates the direction of force on a test mass. That's all. Okay. Now, explain with reference to gravitational field lines why the gravitational field near the surface of the Earth is approximately constant for small changes in height. So this is really important. So suppose this is the Earth. So the gravitational field lines are directed radially inwards, right? However, if you zoom if you zoom into this section over here, this section, if you zoom in, as you come closer to the surface, you'll see that the closer you get, it appears as if, the field lines are parallel, although they aren't because they're converging to a point. But the closer you get to the surface of the Earth, you'll see that, the lines appear to be parallel. Although as increase distance, when you increase distance, you'll see that they aren't parallel because over time the distance increases. But when you're really close to the surface of the Earth, they seem to be parallel. And parallel field lines indicate that field strength is constant, as you've seen in a uniform electric field. So that's the general idea. Now, and if you take a look at the formula for gravitational field strength, which is Gm by r square, it is approximately equal to Gm by r plus h whole square. So if height is much smaller than the radius of the planet, then we can say that gravitational field strength is more or less constant because these two will have the same value numerically. They will almost have the same value because h is much smaller than r. Like compare 1 kilometer to 10,000 kilometers, something like that. It is negligible. So they will have the same value mathematically, right? So these are the 2 points that we need to state, that the change in height is negligible compared to the radius of the Earth. So the field lines appear to be parallel or are effectively parallel. This is a word that they preferred, although it is optional. You can say that. It's fine. Okay, let's move on to the next one. A large isolated uniform sphere has mass m and radius r. Point P lies on a straight line passing through the center of the sphere at a variable displacement x from the center as shown. Okay, so let's take a look at this, right? How do we solve this? Come on. Sorry, it's a bit messy. The magnitude of the gravitational field strength at the surface of the sphere is y. Determine an expression for y in terms of m and r. Okay, so y is the gravitational field strength small g, and the formula for gravitational field strength is Gm by r square, where g is the universal gravitational constant, m is the mass of the planet, okay, and r is the radius of the planet, as they have said. They mentioned this. They mentioned this, that it is mass m and radius r, so it's simply Gm by r square, right? Okay, so that's that. Y is equal to Gm by r square, and capital G is in fact our universal gravitational constant. Next, explain why the surface of the sphere G always has the opposite side to x. This is very important, okay? What does this mean? So suppose this is a sphere. Suppose this is the sphere that we're talking about. We know that gravitational field lines, are directed radially inwards towards the center like this. Now, suppose we are going to move a distance x away from the center. Suppose we are moving a distance x away from the center. So this will be plus x, right? Suppose if we consider right to be positive. So if we're moving to the right, which is positive, the field line is directed to the left, which is negative. Also, similarly, if you're moving to the left, then x is negative. X is negative. But at the same time, the field line is directed to the right, which is positive. Okay. So like if you move away from the planet, the field lines are always converging to the center, right? So they are directed towards the center. So the distance moved and the field strength will always have the opposite sign. That's the logic. Because the force is in opposite direction to displacement. By force, they're actually referring to the gravitational field strength. Okay. So this is one way to answer it. There were other options. And you need to mention something else as well. Okay. Like you need to mention something else over here. So I'll just edit that over here. 1 sec. So the first point that you need to write. Okay. The first point is the gravitational force is always attractive. Okay. So the gravitational force is always attractive. Or you could say that gravitational force always acts towards the center of the sphere. What I was telling you guys. The gravitational force always acts towards the center of the sphere. Fine. This is point number 1. Okay, you need to mention this. This is point 1. If you don't mention this, then you don't get the first mark. So gravitational force always acts towards the center of the sphere. And what about the second point then? So the second point is one of these over here. So you can either say that the force, right? You can either say the force is in opposite direction to the displacement all the time. Like if you go to the right, if displacement is to the right, the force will be towards the left. That's the general idea, essentially. Or there were other options. I don't prefer those. It's like if you say at a point to the right of the center, at a point to the right of the center, force x to the left. Force x to the left. What does this mean? Suppose this is the planet. So at the point to the right of the center, like if you go to the right, at a point to the right of the center, the force x to the left. And at a point left to the center, the force x to the right. That means they will always be in opposite directions, okay? But personally, I prefer gravitational force always acts towards the center of the sphere, and the force is in opposite direction to the displacement, something like that, okay? Next, complete figure 1.2 to show the variation of g. Oh, this is a new theory, by the way. I've never seen this. Like why g always has opposite side to x. Complete figure 1.2 to show the variation of g with x up to plus minus 3r. So they've given us the gravitational field strength in the center of the sphere, right? Now outside, we know that the relation between gravitational field strength is g is equal to minus gm by r square. For some reason, they did not include the minus sign here. Because, no, the reason is they only said magnitude, okay? That's why they did not include the minus sign. But we know that there's a minus sign. Gravitational field strength is always negative due to the attractive nature of the force. So we know that if you double r, g decreases to 1/4 of its value, okay? So check this. If you double r, 2r, g decreases to 1, 2, 3, 4, 5. Minus 0.25 y. 1/4 of the value. 1/4 of 1 is 0.25. And if you triple it, which is 1 by 3 square, 1 by 9, it goes to 0.11. So you know that this is minus 0.1, minus 0.2, 0.3, 0.4, 0.5. So it goes to 0.11, which is just a bit above 0.1. And on the other side of the graph here, since y takes positive values here, then r should be negative, right? Since the displacement is negative, then field strength should be positive. Similarly, on this side of the quadrant, since displacement is positive, it's taking positive values, plus r, plus 2r, plus 3r. The gravitational field strength is taking negative values because it's always opposite in nature, right? That's the main concept. Same sketching, okay? 1, 2, 3, 4, 5, 0.25y, 0.25y, and here 0.1, 0.1, 0.1y. Okay, makes sense, guys? So that's that. This is what you need to draw. Hopefully that makes sense. I'll read out the mark scheme. Smooth curve with decreasing positive gradient starting at r and minus y and reaching 3r with gradient still, with g still negative, sorry, not gradient. Both of the above curves in correct quadrants, and then smooth curve with increasing positive gradients ending at minus ry and reaching minus 3r with g still positive. So g will always be positive there, g will always be negative here. Both of the above curves in correct quadrants, and curve passing through plus minus 2r plus minus 0.25y plus minus 3r and plus minus 0.11y. Okay, that's all. Moving on to question 2. Define specific heat capacity. So this is how they wrote it. Thermal energy per unit mass, change temperature. Thermal energy per unit mass to change temperature. And the second point is thermal energy per unit change in temperature. Thermal energy per unit change in temperature. So you don't need to write it this way. You can write it like it's thermal energy required per unit mass to change the temperature by 1 unit. That also works, okay? Anything is fine over here. Now what? An ideal gas of mass 0.35 kg is heated at constant pressure of 2 into 10 power 5 pascals so that its internal energy increases by 7,600 joules. During the process, the volume of the gas increases from 0.038 meter cube to 0.063 meter cube, and the temperature increases by 56 degrees. So internal energy has increased, and since volume has increased, work is done by the gas, W is negative, so that the magnitude of work done on the gas is 5,000. So it's just magnitude, but if they said the value of work done, it would have been a negative value. So work done is P del V, we know the formula. So pressure is constant at 2 into 10 power 5 pascals, and the change in volume is from 0.038 to 0.063. So the value is actually 5,000 joules. Now, they asked us explain whether work is done on the gas. The work done on the gas is positive or negative. I already told you guys it is negative because the gas is expanding against external atmospheric pressure or something, right? External pressure. So work is done by the gas, or you can say that the alternate one is work is done by gas, or gas does work, right? Gas does work. So work done on gas is negative. So work done on gas is negative. Hopefully I could clarify, guys. Remember these 9 things that I tell you, okay? Volume increase, expansion, work done negative, W negative. Volume decrease, contraction, work done positive. No change in volume, W 0. Temperature constant, internal energy constant. This is for an ideal gas, by the way. Temperature increased, internal energy increases. Temperature decreased, internal energy decreases. Volume, sorry, next, any sudden change where heat cannot enter or leave, that means that if any change occurs suddenly where heat cannot enter or leave the gas, we say that Q is 0. And if heat is supplied to the system, Q is positive. If heat is lost by the system, Q is negative. If it is cooled, basically. Determine the magnitude of the thermal energy transferred to the gas. So I used the first law of thermodynamics, which is del U. This increase in internal energy of a system is equal to the heat supplied to the system and work done on the system. So plus 7,600, because they stated that on top over here, is equal to Q and minus 5,000 because work was done by the gas. So we actually end up with a value of plus 12,600, okay? Now calculate the specific heat capacity of the gas for this process and give a unit with your answer, alright? So we know that Q is equal to mc del theta. We need to find out C. So C is equal to Q divided by m del theta. The value of Q is plus 12,600 joules. The value of mass is 0.35. It's mentioned on top. And the change in temperature is 56 degrees Celsius. The change in degrees Celsius will be the same as the value of change in Kelvin. It's the same thing, okay? So we are just going to use 56, and the unit will be, the value is 640, and the unit will be joules per kg per Kelvin. Change in degrees is the same as change in Kelvin, okay? So, but the SI unit is in per Kelvin, right? Now let's move on to the next one. I think this was a bit hard. Let's try to do this step by step, okay? Let's not mess up. The gas in B is now heated at constant volume. I already told you guys about this. So it's heated at constant volume. So we know that P del V or W is 0 rather than at constant pressure. The increase in internal energy of the gas is the same as before, which is at 7,600 as before, 7,600. Now use the first law of thermodynamics to explain whether the specific heat capacity of the gas for this process is less than, the same as, or greater than the answer in B4, which is 640. Okay. So we need to see the impact on Q. Let's try. So they did not mention anything about internal energy. So we will assume that the change in internal energy is constant at 7,600. We know that del U is equal to Q plus W, and W is 0 over here due to the fact that it changed. The change occurred at constant volume. So W is 0. So it is not working against external pressure. So we just supplied heat to increase the internal energy to 7,600. So since W is 0 and U is still at plus 7,600, the value of Q is also at 7,600. So now we know the new value of Q. Before it was 12,600, now it's 7,600. That's the first step, okay? So you need to mention that. I wrote this extra. This was not in the mark scheme. Del U is equal to Q plus W, and W is equal to 0. So del U is equal to del Q is equal to plus 7,600. Okay. So these are the marking points. Same gain in internal energy. So same temperature rise. This is very important. Because the internal energy change is the same, they did not mention anything about that. Oh no, they did over here. They wrote it. The increase in internal energy is the same. So what impact does this have? Due to the same increase in internal energy, the temperature increases by the same amount, 56 degrees Celsius. So del T is the same. And there is no change in volume, so there is no work done. No change in volume, so no work done. Okay, W is 0. Or there was an alternate wording for the same point. Let me show you what we could write. We could say no work done, so less thermal energy needed. No work done, so less thermal energy needed. For same change in internal energy. For same change in internal energy. What does this mean? Before, we still had the same internal energy change plus 7,600. But since some work was done by the gas, we needed to supply more thermal energy. But here, there's no work that needs to be done against the external atmosphere. So we can supply just plus 7,600, which will give us the same change in internal energy. Okay. So I'm going to repeat again. The change in internal energy is the same. So the increase in temperature is the same, del T. Then there is no work done because the change in volume is 0. So W is 0. So finally, what has happened? If you see, we know that Q is equal to mc del theta. We know that Q is equal to mc del T. So if you make C the subject, which is Q by m del T, we know that the value of Q has decreased, mass has remained constant, del T has also remained constant due to the same increase in del T. Now, since the numerator has decreased, the value of C must also decrease. So there is less thermal energy needed for the same temperature rise. So lower specific heat capacity. That's the logic. You can also explain it mathematically, but these are the 3 marking points. Okay. The second one has an alternate answer, but that's it more or less. Okay. Let's move on to question number 3 then. Remember to like the video, guys, if this content helps you. Also, remember to subscribe to the channel and hit the notification button, the bell, so that you don't miss any videos. I know your exam is on the 13th of May, I think. The physics exam along with S1. I'll be uploading more S1, physics paper 5, physics paper 4, don't worry. I know I missed October, November 2022. I'll upload those as well. And I'll try to release the February, March 2024 paper as soon as it's out, okay? I'll try to upload that as well. And remember to drop down any requests in the comment. And yeah, if you need more help, if you need access to all of these solved things, I know help for the exam, you can subscribe to my Patreon, the second tier, which gives you access to all of these. I'll drop a link in the description. And yeah, that's that. State the meaning of the symbols N, M, and C square. So we know that capital N is the number of molecules of the gas, optional, number of molecules of the gas. Then M, small m, is the mass of one molecule of the gas, also optional. And mean square speed, angle bracket C square, is mean square speed of all the molecules in the gas, okay? Now prove that kinetic energy can be written as 3 by 2 kT. So we know that PV is equal to N kT, and we also know that PV equals to 1 by 3 nmc square. So if we equate these two, you can get rid of capital N. Then you can introduce half on both sides. Introduce half on both sides. Then you end up with this. Then cross multiply the 3 to the left hand side. So you get 3 by 2 kT is equal to half mc square. And half mc square can be written as the mean kinetic energy of each molecule, yeah? Now, what have they said over here? The surface of a star consists mainly of a gas that may assume to be ideal. The molecules have an RMS speed of 9,300. And the mass of each molecule is 3.34 into 10 power minus 27 kg. Determine to 3SF the temperature of the surface of the star. So we know that 3 by 2 kT is equal to half mc square. So 3 by 2 into k, it's from the data booklet, 1.38 into 10 power minus 23 times temperature is equal to half mass of one molecule given in the question, c square, mean square speed, so RMS value whole square. So we get a value of 6980 to 3SF, 6980 to 3SF, okay? Next, they quickly transition to, astronomy. This was added to the syllabus in 2022. So let's learn this properly. The radiant flux intensity of the star is 2.52 times 10 to the power minus 8 watt per meter square, observed at a distance of 4.16 into 10 power 16 meters from the star. Find out the luminosity with unit. So we know that the formula for radiant flux intensity is L by 4 pi d square, where d is the distance and L is the luminosity. All of these are included in the new notes. I've made new notes since 2022. They are very high yield for medical physics, astronomy. PET scan is also included in the notes, if you're wondering. So, and to practice questions from PET scans and astronomy, you can only practice from specimen paper 2022 onwards. All of those are solved in my channel. I'll link them at the end of the video, the playlist. You can watch from there. So 2.52 times 10 power minus 8 radiant flux intensity is equal to luminosity by 4 pi 4.16 in 10 power 16 whole square. As a result, we get the value of luminosity, and the unit for luminosity is watts because it is the total power of radiation emitted by a star. Now determine the radius of the star. So we are going to use the Stefan-Boltzmann constant here. This is the equation that's derived from the Stefan-Boltzmann constant. That luminosity of a star is equal to 4 pi sigma r square t to the power 4, where r is in fact the radius of the star, yeah? So 5.48 times 10 to the power 26, the answer you got from before, is equal to 4 pi times 5.67 in 10 power minus 8. The value of the Stefan-Boltzmann constant, if you're wondering, is given over here. Stefan-Boltzmann law. And the value of the constant is over here, sigma, 5.67 into 10 power minus 8, yeah? So that's the Stefan-Boltzmann constant. So what are we getting? Yeah, 6980 to the power 4 is and r square. We get the value of r, which is 5.69 into 10 power 8 meters. Now, next, the gas at the surface of a star has a very high pressure. Use the basic assumptions of the kinetic theory to suggest why, in practice, a gas at the surface of a star is unlikely to behave as an ideal gas. Okay, so guys, listen. We're going to use like there are a few gas laws, right? Boyle's law states that P is inversely proportional to V. So if you have very high pressure, what happens to volume? It decreases a lot. Okay. So you know that one of the basic assumptions is the volume of the gas molecules is negligible compared to the volume of the gas itself, the container. But if you increase pressure by a lot, the volume decreases due to the increase in pressure, and the gas molecules are closer together, and the volume of the container or the gas itself becomes less. So what do you see here? The gaseous particles, the volume of the gaseous particles literally is much less than the volume of the whole container itself. But here, since the volume is so less, the volume of the gaseous particles is less negligible compared to the volume of the gas, right? So now it is behaving less ideally, rather it turns closer to a real gas. So you need to state that. If you had AS chemistry, this is easier for you guys. But for A2 physics candidates, this is also something you need to know. Gases approach ideal behavior when you have very high temperature and very low pressure. And they approach real behavior when you have a very low temperature due to the formation of IMFs and very high pressure. Okay. So very high pressure, so molecules are very close together. And the volume of molecules is not negligible now compared to the volume of the gas. Or you could talk about, the IMFs, forces between molecules are not negligible now. Forces between molecules are not negligible because the molecules are closer together, so the chances or probability of forming IMFs is higher now. And we know that an ideal gas is not supposed to have any IMFs, right? So that's the general idea. Hopefully you guys get it. But in the first part, remember, the marking the road, you cannot write nearer. Okay, you have to be very specific that at very high pressure, the molecules are very close together. You cannot say nearer. Okay, that is a fault. Okay, moving on to question number 4. Also, if you do have any queries, please feel free to comment below. I do try to reply to the comments as much as I can, but I've been very busy lately since I'm in the final year of med school. Plus, I do tutor students. But I'm letting that go. I plan to focus on medicine as a whole. I'll be done this year, and my YouTube channel more. I have huge plans actually this year. I plan to release a course for you guys, which you can buy soon, for physics, chemistry, bio, and math, all of the components. So yeah, let's see where it goes. Hopefully not this session though, not for the May June 2024 session, but hopefully from the May June 2025 session, you guys can buy it if you subscribe to the Patreon. Anyway, so let's talk about this. A heavy metal sphere of mass 0.81 kg is suspended from a string. The sphere is undergoing small oscillations from side to side as shown in figure 4.1. The oscillations of the sphere may be considered to be simple harmonic with amplitude 0.036 and period 3 seconds. What is meant by simple harmonic motion? So it is basically motion in which acceleration is directly proportional to displacement, and also motion in which acceleration is always in the opposite direction to displacement, or you could say motion in which acceleration is always directed towards a fixed point. Motion in which acceleration is always directed towards a fixed point. Is that okay? Next, calculate angular frequency omega. We know that omega is equal to 2 pi by t. Also, guys, remember to write down the formulas because there is one mark for writing this only. So 2 pi divided by 3.0 seconds. The answer is 2.1 radians per second. Okay, next. Total energy of oscillations. The formula for total energy is half m omega square x naught square. The value of mass is given at 0.81 kg. It is given here, 0.81 kg. 0.81 kg. Then we have the time. We also have the amplitude at 0.036 meters. So that's half m 0.81 times 2.1 whole square omega times 0.036 whole square. Yeah. So that gives you an answer of 2.3 times 10 to the power minus 3 joules. Okay. Next, very important, very important. First time in A2, by the way, we have a situation where there's critical damping. Guys, I've noticed something, by the way. My channel has popped off a bit more compared to the other channels. I really don't know why, especially in physics, though. Not in chemistry or bio much because I don't solve those. I do plan to focus a bit more on math, by the way. So, why do you think what makes my videos special? Why are they doing much better than the other ones? What do you guys think? Just comment below. I'll try to do that more so it helps. I'll try to make these solving sessions more interactive for you guys. And I'll try to improve. If you have any problems with my way of teaching, please do let me know. Anything with the pace. But a lot of students actually complain that the pace is actually too fast sometimes. But my content is supposed to be not for teaching exactly. It's supposed to be at the end of your teaching, at the end of your learning, basically. Like when you're done with everything and when you're just revising before the end of an exam. That's when you should be watching my content. I do plan on making more tutorials though. I'll upload those soon when I'm more free. But yeah, thanks for all the support, guys. It means a lot to me. We are gonna reach 20K subscribers soon. I did plan on doing a face reveal at 10,000 subs, but I think I'm gonna push that behind to like 50K or 100K when I have the silver play button. So yeah, do subscribe to the channel. That would help a lot. Anyway, so first time in A2 where we get critical damping. So the displacement is at plus 0.036 meters initially, and it is then released at time t is equal to 0. The water causes the motion of the sphere to be critically damped. So this is why I drew these three figures on top. I'll tell you, wait. On figure 4.2, sketch the variation of the displacement of the sphere from its equilibrium position from t0 to t equals to 6 seconds. So this is the tricky part. Listen, for light damping, remember, time period is unaffected. Okay, time period is unaffected and the amplitude decreases gradually. Okay, this is normal. This is normal. And for heavy damping, also time period is unaffected, but rather than the amplitude decreasing gradually, it decreases very fast. Like you get one oscillation or 1.5 oscillation, then it stops. But for critical damping, you do not even have the capacity. The damping is so strong that you do not have the ability to perform even one oscillation. So check this. The time period is 3 seconds. So if the oscillation is critically damped, the oscillations should stop almost immediately, even before 3 seconds. Okay, that's the general idea. So that's what you need to draw here. Okay, so the shape of the curve will be totally changed. Wait, let me show you. This is normal, undamped. So this is undamped. This is light damping and this is heavy damping. So that's why they wrote 0 to 6 to trick you, because the examiner wanted to see whether you knew that the shape changes and the oscillation will stop before 3 seconds. Okay, so this is a marking point. Line starting at 0, 0.036 and not reaching plus minus 0.036 at any other time. Smooth curve with no sudden change in gradient, showing continuously decreasing magnitude of x from maximum displacement at t0 to final displacement of 0 where the gradient is also 0. It needs to be flat. It needs to be absolutely flat, okay? It needs to be flat. The gradient reaches 0 and turns flat. It's so hard to draw over here. I'm so sorry. Wait, let me go again. Take 2. Okay, absolutely flat. Hopefully that's fine. Next, displacement reaches final value of 0 between 0.75 and T3 at the latest. So it had to reach T0 between 0.75 and 3. Any time between these. So the general idea is if any oscillation is critically damped, this is 0.036, yeah? It will reach 0 even before one oscillation has taken place. That means since the time period was 3 before, it will reach 0 amplitude even before 3 seconds. That's the general idea. And it should have a smooth curve and decreasing. And you need to continue the line till t equals to 6 because they mentioned that in the question. Okay, these are the 3 marking points. Okay, understood? So it needed to be between 3 and 0.75. Okay, makes sense? Okay, that's good. First time in A2, by the way, so please do this question properly. Important. You might face heavier critical damping. So just remember, in heavy damping, time period remains the same, but rather than many oscillations in light damping, you'll just have like 1 or 2 oscillation and then it stops like this. Okay, this is heavy damping. Sorry. Okay, let's move on. Let's move on to the next one. Give me one sec. So messy. Okay, define electric potential at a point. How many questions do we have, by the way? We have 10. We are currently at 5 at the halfway mark. So, is the work done per unit charge? Work done per unit charge? Yes, so it's the work done per unit positive charge, right? In moving it from infinity to the point inside the field. So it's the work done per unit positive charge to move it from infinity to the point inside the field. That is electric potential. State 3 conclusions that can be drawn about the spheres from figure 5.1. The conclusions can be qualitative or quantitative. Okay, so let's see. So this is a graph of electric potential. So let's take a look at the graphs for electric potential. What do they look like? So for potential, if both are positive, it will look like this. If both are negative, it will look like this. If one is positive and the other is negative, it will look like this. There you go. So clearly this one is negative, the other is positive. So it looks like this, right? Okay. So the charge on the left is negative and the charge on the right is positive. And you know that potential is constant until you hit the radius. So let's look into this. Let's dive deeper, right? Come on. So the radius of the first sphere is, yes. So the radius of the first sphere is, if you check properly, come on, it's in between 0 and 4. So the radius is 2 over here. And here, it's constant till 20. So it's 4. 4 for the one on the right. So we have two isolated middle spheres. What are they? X and Y that are situated near to each other in a vacuum with their centers 24 meters apart. Point P is a variable distance x from the center of sphere x. So this distance x is from the center of sphere x. So since it's from sphere x, x lies on the left. X lies on the left and y lies on the right. So the one on the left is sphere x and the one on the right is sphere y. So we can say that x has a radius of 2 meters. X has a radius of 2 meters. And y on the other hand has a radius of 4 meters. That's what they wrote. So radius of sphere x is 2 meters. Radius of sphere y is 4 meters. and radius of y is double the sphere radius of sphere x. But you can't write all three. You wouldn't get three. You would get a maximum of two from those. Okay, like you could say that radius of y is double the radius of x. So that way you get like 2 out of 3 marks, any two from these. And then other ones include like you could say that the charge of sphere x is negative. Charge on x is negative. Then there's another point. You could say charge on y is positive. Charge on y is positive. Or you could say that spheres carry opposite charges. Spheres carry opposite charges. But also the same. You could only write two from these three. Okay, and two from the top three. So that's a total of 4 points over there. And there's another point. You could say that the magnitudes of the charges on the spheres are equal. Why so? This is because, look at this. Look at the midpoint. Where is it? The midpoint is at the center at 12. From 0 to 24, the midpoint, or the point where potential is, neutral. Potential is 0 is at 12. And we know that the formula for potential is V is equal to 1 by 4 pi epsilon naught into Q by R. So since potential is equal at that point, if you equate it, what do you end up with? Q by R for sphere 1 is equal to Q by R for sphere 2. So since distance is 12 for both of them at the midpoint, so the value of Q must also be the same. So that is another point that you could write, that the magnitudes of the charges on the spheres are equal. You could mention that. That's another point, that magnitudes of charges on the spheres are equal. So any two from these, and yeah, one from that one. Any three works, okay? Moving on, a positively charged particle is now placed at point P such that x is equal to 12 meters. The particle is released. Describe and explain the subsequent motion of the particle. Okay. So x is a positive charged particle, right? X is a positively charged particle. It is located over here. So clearly, it will be attracted towards the negative particle to the left, and also it will feel repulsion from the right. So you can write any of these. Either say particle is attracted to X, or say particle is repelled from Y. And an alternate way of saying this is that the resultant force is on the left hand side. Resultant force on particle is towards X. The resultant force on particle P, on this particle that is placed at P, is towards X. Towards X, away from Y, or to the left. Same thing, okay? Same thing. Anything works. To the left. And the particle accelerates towards X. Same thing. Accelerates towards X, away from Y, or to the left. So do you get the general idea? When they ask you to describe the motion, you talk about the force, you talk about the acceleration, you can talk about the velocity. And as you get closer to x, as you can see, you know that the potential gradient is electric field strength. So the gradient gets steeper as you get closer to x. So what will you say? That the force or the acceleration increases as it gets closer to x. So these are the 3 points. Resultant force is always towards the left due to the attraction towards x. It accelerates towards x, so the velocity is increasing. You could also say that. And the rate of increase of velocity or the acceleration, the magnitude of acceleration also increases. Hopefully that makes sense. Let's move on. Question number 6. Define magnetic flux density B. It is the force per unit length, force per unit current, and the current must be perpendicular to the field. Or you could say the length of the wire, the length must be perpendicular to field. Next, ignore the diagram. It's for a later part. Electrons are moving in a vacuum with speed 1.7 into 10 power 7 meters per second. The electrons enter a uniform magnetic field of flux density 4.8 millitesla. Now, as you can see, it is moving in a semicircle inside the field. So, if the field was everywhere on the paper, it would actually form a circle because it's a semicircle right now. But as soon as it leaves the field, it travels in a straight line again. The path of electrons remains in the plane of the page. State the direction of the magnetic field. How to find this out? Check this, okay? So, since it's an electron, you need to change your middle finger, okay? You need to change the direction of the middle finger. So, for example, we know that the force is always directed towards the center. So, thumb will point down. I'm considering point X, by the way. I'm considering point X. And my middle finger, logically, it should point to the right. But since it's an electron, we need to change the direction of the middle finger to the left. So middle finger to the left and thumb down. So if you do it along with me using your left hand, your index finger should point into the screen at point X. So index finger into the screen at point X, middle finger to the left because it's an electron, we need to use conventional current, and thumb pointing towards the center of the circle, so down. So the direction of the magnetic field is actually into the page. Next, show that the magnitude of the force on each electron is 1.3 times 10 to the power minus 40 newtons. We know that force is equal to BVQ. So the values of B, V, and Q are given on top. B is 4.8 times 10 to the power minus 3 because it's millitesla. V is 1.7 times 10 to the power 7. And Q is the elementary charge, 1.60 into 10 power minus 19. So since data is given to two significant figures, since it's the minimum, we are going to give the answer to two significant figures as well. 1.3 times 10 to the power minus 14 newtons. So there's one formula, one mark for writing the formula BVQ. Next, on figure 6.1, draw an arrow to indicate the direction of the centripetal acceleration of the electron where it enters the magnetic field at point X. So the direction of centripetal acceleration will always be the same as the direction of force, which is towards the center of the circle. So the arrow at point X should be pointing down the page, like this blue arrow that I drew over here, okay? Next, use the information in B2 to calculate the distance d between the path of the electrons entering the magnetic field and the path of the electrons leaving it. So essentially, we need to find out the diameter of the circle. Okay, let's go. So we know that the magnetic force provides the centripetal force. Okay. So we know that the centripetal force is equal to mv squared by r, and bvq provides mv squared by r. So if you equate them, you can get rid of one of the v's, or you know the value of bvq, which is 1.3 times 10 to the power minus 14 is equal to mass of electron 9.11 times 10 to the power minus 31 from the data booklet times 1.7 times 10 to the power 7 whole square. Value of velocity is given here, divided by r. So after you find out r, when you multiply it by 2, since we know that d is equal to 2 times r, you get a value of 0.040. Okay, 0.040 meters. Is that fine? Okay, great. I'm just going to check something. Minus 14. 10 to the power 7 whole square. Yes, okay. If you actually use the exact answer, only then you'll get 0.040. But if you use the rounded off answer 1.3, you actually get 0.0405, which is rounded off to 0.041. So this is actually a bit tricky because usually I do tell you guys that for show questions, I always tell you to use the calculator answer. But for show questions, it's typically suggested that you carry this forward, this exact value forward. But yeah, recently I'm seeing that they ignore this. You can always use the calculator answer. I think that's better. Okay. Always use the calculator answer, then it will always match with the mark scheme. Okay. That's what I've noticed recently from 2023, actually. Next, what do we have? The electrons are in B are replaced with positrons that are moving at 3.4 times 10 to the power 7 meters per second along the same initial path. Now, the speed has doubled. We know that R is equal to mv by bq. They have the same path, same magnetic field, so B remains unchanged. Positrons and electrons have the same charge magnitude, it's just that the sign is different. The mass is also the same, they're antiparticles. Excuse me, sorry. And velocity has doubled. So the value of R must also double. So the radius will now be double, or the diameter will be double compared to the previous one. But the circle will be in the opposite direction because rather than electrons, we're now dealing with positrons. So index finger into the page, middle finger to the right. So the thumb actually points upwards. So the circle forms upwards. And logically, due to doubling the speed, the value of the diameter will also double essentially. So measure this D with a scale and then just take double the length on top and just draw it like how I did over here. Okay. See if that's fine. Is it okay? See if this is okay. All right. Let's move on to question number 7 then. Okay. Question 7. Question on alternating current. We don't have much left. 7, 8, 9, 10 will be done soon. So this is square current, but it's just asymmetrical. Okay, it's asymmetrical. We have a varying current that passes through a resistor of resistance R. Determine expressions in terms of I naught and R for the power dissipated in the resistor for the times when the current is in the negative direction. Okay. So we know that the formula for power is I square R. Okay. So minus I naught square R is I naught square R. The negative value turns positive. Next, when the current is in the positive direction. When the current is in the positive direction, it is at 2 I naught. So it's 2 I naught whole square times R. So that's 4 I naught square R. Okay? Easy. Next, on figure 7.3, sketch the variation of P with time t between t is equal to 0 and t is equal to 2t. Label the power axis with an appropriate scale. Okay. So what you need to understand is, although the value of current may be positive or negative, the value of power will always be positive. So when power is at current is at minus I, power will be at I square R. And when current is at 2I, power will be at 4 I square R. 4 times this value. So 1, 2, 3, 4. Okay. So I've done the scaling according to this. So if this one is at I naught square R, that one will be at 4 I naught square R. 4 times this value. Okay. So at 20 boxes, well, that is at 5 boxes. But P will always be non-zero, yeah? Let's move on to the next one. Use your answer in B to determine an expression for the mean power. So we know that it is the power is at I naught square R for half the time and 4 I naught square R for the other half of the time. So mean power is equal to the average of this since they're at those values for half the time. So I naught square R plus 4 I naught square R divided by 2, that gives us a value of 2.5. 2.5 I naught square R. They actually accepted a fraction for some reason. They accepted 5 by 2 I naught square R. 2.5 I naught square R also works. Now they want the root mean square value. So we know that the formula for average power or mean power is actually uh, RMS value of current, the root mean square value of current whole square times R. So using that, we can find out the value of the root mean square. So IRMS whole square times R is equal to 5 by 2 I naught square times R. You can get rid of R on both sides. So after you square root both sides, you actually end up with IRMS is equal to root over 5 by 2 times I naught. So that's how you did it. So this part actually, this is actually unique. I haven't seen this before in the paper. This is new in A2. So yeah, be careful and learn how to do this. Because if they give you square current, this is how you deal with it, okay? Because typically, you know that for square current, if it was symmetrical, right? Like if this was I naught and this was also minus I naught, if it was symmetrical like this, then you guys know, you'll see this in my notes on Patreon if you have access to those, that the RMS value of square current is the same as the peak value. But the issue here is that the graph is not symmetrical. It's like this, which is why we cannot do it directly, which is why we had to do it in this manner, like finding out the average power first and then using that to find out RMS. This is why we had to take the longer route. All right, anyway, I think we should move on to question number 8. We're almost done with the syllabus. So show that the momentum of a photon of electromagnetic radiation with wavelength is given by P is equal to h by lambda. So this mainly deals with the de Broglie wavelength, which you guys know already, is the wavelength associated with a moving particle. So question number 8 is very tough, very hard, very high yield for us. So I want your absolute focus right now, okay? So let's go for this. So P is equal to E by C. This formula is actually included in our syllabus. It's in the syllabus. P is equal to E by C. P is equal to E by C. So it actually states that the momentum of a particle is equal to the energy, the momentum of a photon is equal to the energy of the photon divided by the speed of light. How? You know that P is equal to E by C and E is equal to hc by lambda. So if you substitute that inside, P is equal to hc by lambda by C, you can get rid of these two C's and ultimately end up with P is equal to h by lambda. So if you're wondering how did P is equal to E by C come to be, it actually came from Einstein's equation E is equal to mc squared. You can break down E is equal to mc squared like this. E is equal to mc times c, and mc, mass into velocity, is the momentum. So P is equal to E by C. That's the origin of this formula. P is equal to E by C, yeah? Okay? Anyway, use the expression in A1 to show that a photon in free space that has a momentum of 9.5 times 10 power minus 28 newton second is a photon of red light. Okay. So we know that the photon is moving in free space, which is a vacuum, and we know that the momentum of the particle is 9.5 times 10 to the power minus 28 newton seconds. So we can use this formula, P is equal to h by lambda. So we actually end up with lambda is equal to h by p, 6.63 times 10 power minus 34 divided by p, 9.5 times 10 power minus 28. So we get a value of 700 nanometers, which is actually 700 times 10 to the power minus 9 meters. So it's red light. We know that 700 nanometers in free space is actually red light according to the visible light spectrum. Yeah. Let's move on then. A beam of red light of intensity 160 watts per meter square is incident normally on a plane mirror as shown in figure 8.1. The momentum of each photon in the beam is 9.5 times 10 to the power minus 28. So let's go for this step by step. Okay, this is hard, so be careful. all of the light, this is a new question by the way, first time. All of the light is reflected by the mirror. Key point. All the light or the photons are reflected by the mirror in the opposite direction of its original path. And the cross-sectional area of the beam is 2.5 times 10 to the power minus 6. Show that the number of photons incident on the mirror per unit time is 1.4 times 10 to the power 15. So let's go step by step, okay? So the first mark is for writing the formula for intensity. Intensity equals to power by area, or power is equal to intensity into area. So as I've stated, intensity is equal to power by area. And what is the source of this power? All the photons, right? All the photons hitting the mirror per unit time. And all the photons have energy E, right? So if you multiply N and E, you are going to get the total energy. And if you divide by the time, you're going to get the power. And if you divide by the area, you're going to get intensity. This is the general formula that you need to use. Intensity is equal to power by area. And how do you find out power? Power is the number of photons per unit time times the energy of each photon. This is the general idea. This is the equation for power. So electron volts per unit time. So show that the number of photons incident on the mirror per unit time is 1.4 times 10 to the power 15. Okay. So let's do this step by step. Okay. Let's not mess up. So intensity equals to number per unit time times energy of each photon divided by area. So we know that the intensity is 160 watt per meter square. We know that the area is 2.5 times 10 to the power minus 6. We don't know the number per unit time. That's what we need. And we don't know the energy yet, but we can find it out. What's the formula for energy? It's either hc by lambda. You can do that. That's a far-fetched process, or hf. Or you can just simply go for P is equal to E by C. So energy is equal to P into C. We know that energy is equal to P into C. You have access to the speed of light since it's in free space, and you have access to the momentum of each particle. So if you make n by t the subject, you actually end up with 160 times the area, which is 2.5 times 10 to the power minus 6, divided by the energy, which is Pc. Because P is equal to h by lambda, right? Look, you know that energy is equal to hc by lambda, or h by lambda into c. And you know that P is equal to h by lambda. Does it make sense now? So energy is equal to Pc. That's the concept. So you have access to the momentum and the speed of light, 3 times 10 to the power 8. So you actually get the value of n by t, which is 1.4 times 10 to the power 15. Okay. This isn't the first time that this came, but you know, this proof, first time that I saw this proof, P is equal to h by lambda, using P is equal to E by C, it is included in the syllabus, so you need that. And also, the way that we found out the energy here using PC, that's also new, okay? So this is something new. Use the information B1 to determine the pressure exerted by the light beam on the mirror, okay? So pressure is defined as force per unit cross-sectional area, perpendicularly basically. And we know that force is defined as the rate of change of momentum. So let's go for this step by step, okay? No messing up. So we write down the formula for pressure, which is force by area. Write this down. Pressure is force by area. Pressure is force by area, and force is the rate of change of momentum. These are the two key points. By definition, force is the rate of change of momentum. These are our key points. Pressure is force by area, and force is the rate of change of momentum. So we have access to area. We don't have access to the rate of change of momentum yet, but we can find it out. Let's do that. How? So we know that we have the number of photons per unit time. So if you multiply n by t with del p, you're going to get the force. Okay. So from this question, we have two key points. Yeah. One of them is intensity is power by area. So that's the number per unit time of photons times the energy of photon, each photon divided by area. And similarly, pressure is force by area. So pressure is the number of photons per unit time times the change in momentum divided by area. These are the two things that we need to know. Now, hear me out. Basically, I have never seen this question before. Usually, what they say is, in the past 22 years, I've seen that. They say that when the photons hit the surface, they just stop. They get dissipated. So all the momentum is converted to zero. So we just take the initial momentum. But here we have a mirror. So what's the impact? Due to the mirror, it says that it is reflected in the opposite direction. So it's like kind of those math you did in AS. Like when a ball hits a mirror and then it gets deflected back. So if it was plus p here, it is minus p now. So the change in momentum is minus p minus plus p. So the net change is minus 2p. So the change in momentum is twice the initial value. Get it? So you can find out the pressure like this. Number per unit time of each photon times the change in momentum, which is the initial momentum 9.5 times 10 to the power minus 28 times 2 divided by the area, which will give you a pressure of 1.1 times 10 to the power minus 6. See if it makes sense. Okay. This is how you do it. Wait up 1 second. There you go. This value over here, this is our force. This is the force. And pressure is basically equal to force by area. So we just put that in over there. Okay. Make sense? Next, let's move on. Now the hardest part. The beam of red light, the one which has 700 nanometers, is now replaced with a beam of blue light of the same intensity. This is so important, right? So I just want to explain whether the pressure exerted on the mirror by the beam of blue light is less than the same as or greater than the pressure exerted by the beam of red light. Okay. So let's not mess up. Let's go step by step. So we know that P is equal to H by lambda. Okay. That's the first idea. So since lambda has increased compared to before. Wait, before lambda was 700 nanometers for red light. Now it's blue light. So it's something like 400 nanometers. So lambda has decreased. So P must increase since they're inversely proportional. So that's step number one. Okay. Since lambda, blue light, for blue light, lambda has decreased, P must increase. So that's what we write initially. The photons have greater momentum. But now the tricky part comes, okay? So what's the tricky part? They mentioned a point over here. Wait, let me show you. They mentioned this part over here. Same intensity. Like this. So we know that P is equal to H by lambda. Blue light has 400 nanometers, so lambda has decreased, so P has increased. But we need to keep intensity constant. What do I always teach you from quantum physics? Intensity is number of photons per unit time times the energy of each photon. And by area, of course. And you know that energy is basically PC by the area. So look, if we want to keep intensity constant, area is constant, and lambda has decreased for blue light, and momentum has increased. Speed of light is constant. So momentum increased, right? So energy has increased. But if I want to keep intensity constant as well, then to balance that out, what do I need to do to n by t? N by t, number of photons per unit time, has to decrease. As a result, their product gets balanced out. So these are the first 2 points. Since the photons have less wavelength, they have greater momentum. But to keep intensity constant, right? Since momentum has increased, but the number of photons per unit time has to decrease. Okay. So photons have greater momentum or fewer photons per unit time. That's the first one. Okay, let me rewrite this answer for you guys. I think that will be better for everyone. So the first one is photons have greater momentum or fewer photons per unit time. Fewer photons per unit time. That is point number one. And for point number two, what do we need to state? Greater photon momentum. Okay. Greater photon momentum. So let's talk about pressure. What happened to pressure? Okay. Pressure is force by area. Area remains constant. The change in momentum has increased, right? It was basically del P, which is P times 2. Basically here pressure was N by T times P times 2 divided by area. Now area has remained the same, 2 has remained the same. P has increased and N by T has decreased by the same factor so that it cancels out, so that the intensity remains constant. So suppose if P has increased by 1.3 times, number has to decrease by 1.3 times. So these 1.3 gets cancelled out, these 1.3s, right? So the value of pressure will actually remain constant. So you have to state that greater photon momentum, but smaller number of photons per unit time. Smaller number of photons. Oh, sorry. Smaller number of photons per unit time. So pressure is the same. This is a very hard and high yield question. Please see if you get it. I tried to break this down as easily as possible. Let's go again. Blue light compared to red, it has less wavelength. So since wavelength has decreased, P has increased by a certain factor. But they said that intensity has remained constant. So area is constant, intensity constant, C constant. So if you increase P, the only way to keep I constant is by decreasing N by T. Okay. So N by T has decreased by the same factor that P has increased by. So what happens to pressure? Area constant, change in momentum is constant. Actually, change in momentum is increased by a certain factor. But we know that N by T has decreased by the same factor. So those factors cancel out and the value of pressure remains the same. Okay. So it was a trick question actually. Okay. Let's move on to question number 9 and 10. Last two. I actually need to solve these. I haven't solved these yet. What is meant by nuclear fusion? Okay, let's go for this. Nuclear fusion is when two small nuclei join together. Two small nuclei join together to form one larger nucleus. To form second marking point. To form one larger nucleus. Okay, very good. On figure 9.1, sketch the variation of binding energy per nucleon with nucleon number A for values between 1 and 250. So who's the king of the hill? Iron 56, right? So since this is 250, like halfway, somewhere in between here, right? This is half, is 125. What's half of 125? It is 62.5. This is 62.5. So 56 should be somewhere around here. This is 56 basically. right? Somewhere a bit closer, somewhere over here, I guess, somewhere like this, 56. So this should be our peak. This should be our peak. So we should have a steep initial positive gradient on the left of the peak, and on the right it will be shallower. But it does not return to zero, okay? And even hydrogen, okay? Like, if you think about it, if you are a single proton, what's the value of binding energy? It will be zero, right? When do you have binding energy? When you have more than one proton inside the nucleus. Okay, that's the general idea. So a proton has zero binding energy, a proton or hydrogen essentially. So it's kind of like this. It will go like this, it will increase, and then it reaches the peak at 56, and then it decreases like this, but it will not reach zero. Okay. So the king of the hill is iron 56. The binding energy is 0 at 1 because hydrogen has no binding energy. Okay. Because it's simply a proton. On your line, label a point X that could represent a nucleus that undergoes alpha decay. A point Y that could represent a nucleus that undergoes nuclear fission. Okay. So anything on the left of iron 56, anything on the left of iron 56 typically undergoes fusion. So what typically undergoes fusion? Something like hydrogen or helium. Okay. So anything that undergoes fusion, that's point Y. So something like this, somewhere over here. This is a point Y. Okay. And something that's big, like uranium or something, to the right of the peak, that undergoes fission. So something like this, okay? Anything that's a bigger nucleus undergoes fission, breaks down to form alpha particles, beta particles, etc. Okay? On the right of the peak, fission. On the left of the peak, fusion. A nucleus Z undergoes nuclear fusion to form strontium and xenon, according to this equation. Table 9.1 shows the binding energies of strontium and xenon. The fission of 1 mole of Z releases 1.77 times 10 to the power 13 joules of energy. Determine the binding energy per nucleon in mega electron volts of Z. Okay, let's do this. Okay, step by step. So at first, we need to find out the energy released for one molecule, not 1 mole. Okay, so let's find that out. The energy released from one nucleus will actually be equal to 1.77 times 10 to the power 13 divided by the Avogadro constant, since it's 1 mole. We get this value, 2.94 times 10 to the power minus 11 joules. Next, we need to convert this to mega electron volts, right? But they did that at the end, but that's fine. That's fine. So this is the energy released from one reaction as a whole. Okay. So we know that there is some binding energy on the right and there is binding energy on the left. So if you subtract those binding energies, you actually get this energy released. Okay. So it's like this. Look, binding energy of strontium plus xenon minus binding energy of Z is equal to the energy released. So let's go for it. That's the binding energy in total, right? Binding energy in total, not the binding energy per nucleon. So it's 1.25 plus 1.81 times 10 to the power minus 10. Okay. Minus the binding energy of Z. That is equal to the energy released, which is 2.94 times 10 to the power minus 11 joules. So if you subtract this now, you'll get the binding energy of Z. Okay, you get the binding energy of Z, which is basically this, right? This minus the energy released in the equation, right? Okay. So what do we get overall? It is actually 2.77 into 10 to the power minus 10 joules. Okay. Now what? We need to find out the binding energy per nucleon. So what's the binding energy per nucleon? We need to find out the nucleon number first. It's so tricky. Okay, check this. Let's balance this. So the net charge on the left it's 0, on the right it's 38 plus 54. 38 plus 54, which is 92. And the charge, sorry, the mass, right, on top. On the right it's 2 plus 139 plus 93, 234 on the right. On the left it needs to be 234 as well. 234 minus 1, which is 233. Okay, that's the nucleon number. We should show the working, I guess. Let's show the working. Nucleon number of Z is actually equal to 93 plus 139 plus 2 on the right hand side, which is 234 minus 1 on the left. So it is 234 minus 1, which is 233. So let's find out the binding energy per nucleon. So binding energy per nucleon in mega electron volt is actually 2.77 times 10 to the power minus 10 joules divided by 233 divided by 1.60 into 10 power minus 19. I've converted to electron volts, and to convert it to mega electron volts, what do we need to do? Into 10 to the power minus 6. So that will give us an answer of 7.43 mega electron volts. 7.43. I hope that's okay. So very long math, 4 marks for each of the 4 steps. Okay. First time I've seen a math like this, so you should be ready to face these in the future. I broke it down more than the mark scheme though. They didn't write this line over here. Okay, I broke it down for you guys. Anyway, moving on to the last question of the day. Medical physics. Ultrasound and X-rays are both types of wave that are used in medical diagnosis to form images of internal body structures. Complete table 10.1 for each type of wave. The method of production of the wave, and whether the wave that is detected and used to form the image is the wave that has been absorbed, reflected, or transmitted by the internal body structure. Okay, so ultrasound. How do we produce it? With the help of a piezoelectric crystal. The vibrating quartz crystal. That is how we form it, by using the vibrating quartz crystal. And the detected wave, we actually detect the reflected wave, right? The one that's reflected from the skin, basically. The reflected wave, right? Okay, that's good. Next. For X-rays, what do we use? In the X-ray tube, high-speed electrons hit a target middle, right? So we need to say that electrons, high-speed electrons, hitting a metal target, high-speed electrons hitting the metal target. And which one do we detect in the X-ray? Suppose this is the body, the X-ray will pass through it. So in the bone, it gets stuck, and in other parts of the body, it goes through. So we are actually detecting the transmitted wave, right? So the detected wave is actually transmitted through the body. But in the case of ultrasound, we actually detect the piezoelectric crystal, the quartz is actually a transducer. We don't actually detect the transmitted one, but rather the one that is reflected from the body. This is a key point that we need to know. Very important table over here, okay? Production and which one is detected, either the absorbed one, reflected one, or transmitted one. Yeah. Next, for one type of wave passing through tissue, the wave has 72% of its initial intensity after it passed through 6.2 cm of the tissue. Calculate the linear attenuation coefficient for this wave. Okay, so we are going to use the formula. Which one? I is equal to I naught e to the power minus mu x. So we know that the value, we have 72% of the initial intensity. What does that mean? I by I naught is 72% of the initial. So we can write I by I naught is equal to e to the power minus mu x. I by I naught is 0.72 is equal to e to the power minus mu times, it's in per cm. So mu times 6.2, we can introduce ln. So ln 0.72, ln 0.72 is equal to minus mu times 6.2. So if you solve the math, you're going to get a value of mu is equal to 0.053 per centimeter. 0.053 per centimeter. Okay, that's good. Next, another wave of the same type is in B1 passes through 9.3 centimeters of the same tissue. Calculate the percentage of the initial intensity that is attenuated. Remember, using this formula, you do not get how much is attenuated, but rather how much is transmitted. So to find out the one that is absorbed, okay, so using this formula, like we had 6.2 centimeter, we found out that this is I naught. We found out that I by I naught is actually 72%. So the one that is attenuated is actually 28%. So to find out the 28%, we need to just subtract from 100%. Okay. So in this question, they're asking how much was attenuated. So we're going to use the same formula again. I is equal to I naught e to the power minus mu x. But now I'm going to find out I by I naught first. I by I naught is equals to e to the power minus 0.053 times the distance, which is 9.3 cm. Let's do it. E to the power minus 0.053 times 9.3, which gives me a value of I by I naught is equal to 0.61, 61%. So let's find out the percentage that is attenuated. How? Basically, 100% times 1 minus 0.61. So that is going to be 0.39. 100 times 0.39, which is actually 39%. So 39% has been attenuated. This is how you need to do it. So please be careful what they ask. Do they ask you for the fraction or the percentage of the transmitted wave, or the one that is attenuated by the medium itself? All right. So guys, hopefully that is it. It was overall more or less difficult paper. Some parts were hard, some parts were easy and straightforward, which explains why the threshold was so high. Hopefully I could help you guys. If you do like the content, please remember to subscribe to the channel. A lot of you haven't subscribed yet, so if you do, it will help me a lot. Like the video, it helps with the algorithm a lot, and obviously share with your friends, all right? Also, yeah, if you need more help, personalized meetings with me where we solve your problems, please do consider supporting me on Patreon. And you can also get access to all of these solved papers and my notes, which are a hack for the exams. You can just take it for a month before your exam and then cancel the subscription after you're done with the exam, which helps a lot. It's just $20 for a month. So yeah, I'll give a link in the description, and you can also email me. My email is, it's on my YouTube page, the one with the links. You can email me there if you have any queries, and you can just contact me on Patreon if you need more help. And a quick shout out to my top tier patrons for the month. We still have Deva supporting me. He also has an exam next month, like a lot of you guys. And we have a new patron, Tim. He's been supporting me recently. We had a few meetings. So if you want your name featured on the end page, please do support me on Patreon on the highest tier, the ultimate learning experience. Anyway, that's been it. I'm gonna link the paper for October, November 2023, paper 4.2 up here, and the paper for May, June 2023, paper 4.1, or May, June 2023, paper 4.3 down here, and the playlist for physics, paper 4 up here. And remember to hit the subscribe button. See you guys. Bye bye. Tata.